We're going to look at how to take the combination of items. To take a combination, the order does not matter. Items are selected from the same group, and no items are used more than once. For example, Cold Stone offers 31 different flavors of ice cream. One of its items is a bowl consisting of 3 scoops of ice cream, each a different flavor. Does the order matter here? Let's say that your bowl of ice cream contains 3 different flavors, 3 different scoops. What we're trying to say is it doesn't matter if he puts the vanilla in first, then the strawberry, and then the chocolate, or if he puts in the chocolate first, and then the strawberry, and then the vanilla. Either way, all 3 flavors are in the bowl. So all we really need is how many ways out of 31 could you choose 3 different flavors. For a combination, 31 would be your n. It's your total number of items to be chosen from. And 3 would be your x value. It's the number of items that you're picking out. So a combination of n things taken x at a time is the number of possible combinations if x items are taken from n items total. Notationally, we write this as n choose x. And the formula says to do n factorial divided by x factorial times n minus x factorial. This is the general formula that we will be using to work out combinations. Let's work through some examples using our combination formula. For example, let's say we're trying to work out 7 combination 3. According to the formula, this would be 7 factorial divided by 3 factorial times 7 minus 3 factorial. The first thing you should do is work out the parentheses. 7 minus 3 is 4, so we'll write this as 7 factorial divided by 3 factorial times 4 factorial. Next, you should start writing out what 7 factorial means. It means 7 times 6 times 5, and multiplying all the way till you hit 1. 3 factorial means 3 times 2 times 1, and 4 factorial means 4 times 3 times 2 times 1. If you look, the 4 times 3 times 2 times 1 occurs in the numerator and denominator, so we can cancel these values out. Also, 3 times 2 is 6, and in the numerator there's also a 6. So in the end, the only values you're left with are 7 and 5, and 7 times 5 is 35. So we now know the value of 7 choose 3 is 35. To do this on the calculator, you could simply hit 7, then hit Math, come over to Probability, and scroll down till you see NCR. Then type in your number 3. So 7 combination 3 is 35. Here's the second example. Let's work out 9 choose 5 times 4 choose 1 divided by 13 choose 6. Let's go to the side and work out 4 choose 1 first. This means to do 4 factorial divided by 1 factorial times 4 minus 1 factorial. This would be 4 factorial divided by 1 factorial is 1, so it goes away. And 4 minus 1 is 3. If you think about the definition of 4 factorial, it means 4 times 3 times 2 times 1. And the definition of 3 factorial means 3 times 2 times 1. So what we can see is the 3, 2, 1 in the numerator and denominator cancel, which means 4 choose 1 is simply the number 4. Now let's work on 9 choose 5. This is 9 factorial divided by 5 factorial times 9 minus 5 factorial. 9 minus 5 is 4, so let's replace this. There's a shortcut to working out these factorial problems. What you want to do is start expanding the numerator and write out values till you hit the larger of the denominators. Out of 4 and 5, 5 is larger, so we'll start at 9 and multiply till we hit 5. Make sure you attach the factorial sign once you hit the larger of the denominator values. And now the 5 factorial and the 5 factorial cancel out. Once you cancel the larger of the denominators, expand the remaining denominator. 3 times 2 is 6, and in the numerator there's a 6. We will cancel these. And 8 divided by 4 is 2. So in the end, we're left with 9 times 2 times 7. This is 126. Lastly, we'll work out 13 choose 6. This is factorial of 13 divided by factorial of 6, factorial of 13 minus 6. 13 minus 6 is 7. Next, you want to start expanding the numerator until you hit the larger of the two denominator values. Out of 6 and 7, 7 is larger. So we'll expand the factorial till we hit 7. Make sure you attach the factorial symbol indicating that the values continue to 1. 7 factorial and 7 factorial cancel. So we'll remove these from the problem. Next, you should expand the 6 factorial. Try to look for items that could cancel. For instance, a 4 and a 2 multiply to 8, and these could cancel with the 8 in the numerator. The 5 cancels with the 10, the 6 cancels with the 12, and the 3 cancels with the 9. So you're left with 13 times 2 times 11 times 2 times 3. This comes out to 1,716. We'll put this value in the denominator. Finally, we can multiply the two numerator values and divide by the denominator. This lets us know that the final answer is 42 out of 143. Binary data are data consisting of two outcomes, or two potential responses, such as a yes or a no, or a success or failure. The way we calculate probability for binary data is with the binomial distribution. There are 4 requirements that must be met in order to be a binomial distribution. There must be two outcomes, either a success or failure. Bi usually stands for 2. The next requirement is there a fixed number of trials. We call these fixed number of trials n, and that occurs next in the notation. Next, we need a constant probability of success. The probability of failure would be 1 minus the probability of success, and this is often denoted by q. In the notation, the probability of success occurs here. The last requirement is that all the trials must be independent. This is the only thing that you'll have to memorize because it doesn't appear in the notation. When we're measuring outcomes, we always measure outcomes by the number of successes. So our random variable x represents the number of successes in a trial. The formula to calculate probability for the binomial distribution is the probability that a random variable, capital X, equals a number, little x, is n combination x, probability of success raised to the x power, and probability of failure, which would be 1 minus the probability of success raised to the n minus x power. The x values that you're allowed to plug in go from 0 to n. For example, determine whether the binomial criteria are met. The probability a cow has trig is 1%. A random selection of 20 cows, each from a different herd, are tested for trig. Let x equal the number of these cows that test positive. Let's go ahead and set up notation while we check if the binomial criteria are met. We know x is the number of cows that test positive, so our probability of success should be the probability that a cow tests positive. Our random variable x will have a binomial distribution if there are two potential outcomes. We remember this from the bi and binomial. The two outcomes are either the cow tests positive or the cow tests negative. So this requirement has been met. The next thing that's written in the notation is the sample size. It says that 20 cows were randomly selected. This tells us that there's a fixed sample size of 20. The final thing that we need to put into the notation is the probability of success. And the probability a cow has trig is 1%. Always write this as a decimal, so we'll fill in 0.01. And in our requirements, we can say that there is a constant probability of success. The final condition that must be met you'll have to remember because it does not appear in the notation. And this final condition is independence. Usually living subjects are independent. This includes humans as well as cows. You'll have to justify whether the independence assumption has been met on the exam. You could say a statement to the effect of, one cow testing positive or negative would not affect another cow testing positive or negative, since each cow was randomly selected from different herds. Here's a second example. Determine whether the binomial criteria are met. Let us say that a sample of 5 people bitten or attacked by dogs is selected at random from the population list. Let x equal the number of people in the sample under the age of 12 who were bitten or attacked by dogs. Let's check criteria as we set up the notation. The first portion of the notation is the binomial. This reminds us that there should only be two outcomes, and the outcomes here would be either that a person under the age of 12 was bitten or not bitten. We could summarize this as just a yes-no situation to the question, were you bitten? The next item that appears in the notation is the sample size. It says that a sample of 5 people were chosen, so we know that our sample size is n equal 5. This lets us say there are a fixed number of trials. The next requirement in the notation is a constant probability of success. If you look in the word problem, nowhere does it mention a probability of success, so the exact value is unknown. However, we know that each human should have an equal chance of being bitten or attacked by dogs, so we know that the probability of success would be constant, even if we don't know its exact value. The final requirement to be in a binomial situation is independence, and this is the one that you'll have to remember because it doesn't appear in the notation. On the exam, you'll need to justify this assumption instead of just writing the word independence. An example of justifying it in this situation would be to say that one child being bitten or attacked by a dog under the age of 12 would not affect another child being bitten or attacked by a dog. Therefore, the two people are independent. Each year, almost 5 million people are bitten or attacked by dogs. Children are frequent victims of dog bites. In fact, 60% of all dog bite victims are children under the age of 12. Tragically, of the 33 dog bites that resulted in death last year, 20 of these fatalities were young children. Teach young children to be careful around pets and to never approach a dog they do not know. Always ask the dog's owner for permission before petting any dog. Let us say that a sample of 5 people bitten or attacked by dogs is selected at random from the population list. Let X equal the number of people in the sample under the age of 12 who were bitten or attacked by dogs. The first thing we should figure out is what the sample space is. If we have a sample of 5 people, the potential outcomes could be that no one was bitten or attacked by a dog, or one person could be, or 2 people, or 3, or even all 5 people. This would be our sample space. We could also go ahead and fill out notation. We're aware that this does satisfy the binomial criteria, and we already knew the sample size, n, was 5. We now can also find the value of p. Coming up to this paragraph, it says 60% of all dog bite victims are children under the age of 12, so we know that p equals 0.6. Create a probability distribution. Remember, a probability distribution needs to have your set of outcomes and the probability of each outcome. We found the sample space, so we know the outcomes are that no child could be bitten by a dog all the way up to all 5 children. We now need to find the probability of each of these occurrences. To do this, let's go back to our formula to calculate probabilities. We said that the sample space was 5, or that n equals 5, so we could come up into the formula and replace n. We also know that the probability of success, p, is 0.6, so we can come into the formula and replace p by 0.6. Lastly, 1 minus 0.6 is 0.4, so it would simplify things for us if we go ahead and write that in. Now to calculate the probability of any particular outcome, all we have to do is plug in the number x. The probability that x equals 0 would equal 5 choose 0, 0.6 to the 0, and 0.4 to the 5 minus 0. 5 choose 0 would be 5 factorial over 0 factorial times 5 minus 0 factorial. This is 5 factorial over 0 factorial, 5 factorial. The 5 factorials cancel, and 0 factorial is 1. So this answer is just 1. 0.6 to the 0 power is also 1. 5 minus 0 is 5, so we'll write this as 0.4 to the 5th power. And going to the calculator and typing in 0.4 to the 5th power, you'll get a rounded answer of 0.01. This is the value that we'll put in our probability distribution. We need to repeat these steps for all the values in the table. We'll use the calculator to do this. To find this on the calculator, you would type in 5, math, probability, NCR, 0. Then we want 0.6 to the 0 power, and we want 1 minus 0.6 raised to the 5 minus 0 power. Now again, I'm showing you all the steps needed to calculate this probability. There's some things you could have figured out in your head. 1 minus 0.6 is 0.4, 5 minus 0 is 5, but I'm doing this for if you had large complicated numbers to work with. Now we know that we're going to have to repeat this process for x equals 0, 1, 2, 3, 4, and 5. I'm going to show you a shortcut to automatically calculate your probabilities for these amounts using the formula. To do this, you could go to y equals. Remember, if you have a plot turned on, turn it off, and clear out your y list. The formula that we could type in is 5 choose x. We want to multiply this thing by 0.6 to the x power. And then we want to multiply this by 0.4 to the n minus x power. So by 0.4 to the 5 minus x power. Then hit second table set. Double check that you're in ask mode. So on independent variable, hit enter to be in ask mode. And then hit second table. If you type in the number 0, you get back the same probability. If you type in 1, 2, 3, 4, and 5, you'll get the probability distribution values that we were looking for. There's one last way that you could have worked this out on the calculator. You could have hit second distribution and scrolled down till you see binomial PDF. That's right here, and hit enter. The steps are to enter your n, which is 5, comma, then your p, which is 0.6, comma, and then the x value you're interested in looking at. If you're interested in the probability that x equals 0, you would type that in. If you hit second entry, it'll pull this up again, and you could come up here and change the 0 to 1. This would be the probability that x equals 1. And then if you hit second entry and repeat this again, this would be the probability that x equals 2. So you have 3 options to get this answer. Option 1, you could work it out by hand to get the calculator to reduce it. Option 2, you can use your equation in the table. Or option 3, you can use your binomial PDF command call. I've copied the values that we got from the calculator onto this page. Let's use this to create a histogram for the probability distribution. We'll put our outcomes on the horizontal axis and our probabilities on the vertical axis. Our outcomes are 0 through 5. Looking at our probabilities, the highest probability seems to be 0.3. So we'll run on a scale of 0.1s. The probability of 0 is 0.01. The probability of 1 is 0.077. For 2, it's 0.23. For 3, it's 0.346. For 4, it's 0.259. And for 5, it's 0.078. Notice that I've taken care to leave spaces between each of the bars. This is because the binomial distribution is discrete, so there are no values between 2 and 3, only exactly the number 2 and exactly the number 3. What is the probability that at most 3 people under the age of 12 were bitten or attacked by dogs? Notationally, we should write this as the probability that x is equal to 3 or smaller. This would equal the probability that x equals 0, plus the probability that x equals 1, plus the probability that x equals 2, plus the probability that x equals 3. If we come over to the table, we can see the values. The probability that x equals 0 is 0.01. The probability that x equals 1 is 0.077. For 2, it's 0.23. And the probability that x equals 3 is 0.346. Summing these values, the final answer is 0.663. What is the probability that between 2 and 4 people inclusive, so probability that inclusively between 2 and 4, under the age of 12 were bitten or attacked by dogs? This is the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4. Coming into the table, the probability that x equals 2 is 0.23. The probability that x equals 3 is 0.346, and the probability that x equals 4 is 0.259. The final answer comes out to be 0.835. We need to go through some notation and formulas for these problems. The population proportion is the symbol p. This is what we've been using in the notation x binomial in p. It's the proportion for everyone. The formula to calculate p would be the number of successes in a population out of all members of the population. The sample proportion is p hat. This is what we usually are able to find and know. P hat is your number of successes in the sample out of your sample size. This is an important formula that you'll need to refer back to. The average for binomial distribution is represented by the symbol mu, and the formula for it is to multiply n and p. The sample mean is x bar, and the formula for it is n times p hat. The symbol for population standard deviation is sigma, and the formula for it is the square root of n times p times 1 minus p. The symbol for sample standard deviation is s, and the formula is the square root of n times p hat times 1 minus p hat. You'll probably be using the mu and the sigma formulas the most, and these are formulas that you need to have memorized, along with the formula to calculate p hat. For example, trich infection of cattle is a devastating disease for cattle producers. When diagnosed in a herd, it causes economic loss. The 4 most important risk factors are bull exposure from neighboring pastures and herds, cows commingling with neighboring pastures and herds, new bull additions without testing, non-tested bulls, retaining open cows into the next breeding season. When a cow becomes infected, the following can happen. The cow can become pregnant, but then early in the pregnancy she aborts and comes back into heat. The cow can carry the fetus to full term, can remain infected, and shed the infective trich protozoan after calving. The probability that a cow has trich is 1%. A random selection of 20 cows, each from a different herd, are tested for trich. Let x equal the number of these cows that test positive. We've already verified that this is a binomial distribution. Let's go ahead and write out our notation again. To find the sample space for this distribution, we need to recognize that 20 cows were selected at random and then tested for trich. This means that none of the cows could come back positive. One of the cows could, 2 of them could, or 19 could, or even all 20 could come back as positive. Notice I put brackets on the outside of these numbers. The brackets turn a series of numbers into a set. Without the brackets, this would not represent a set. To find the standard deviation, we'll use the formula that sigma equals the square root of n times p times 1 minus p. Our sample size was 20 cows, and the probability of testing positive was 0.01. So the probability of testing negative is 1 minus 0.01. This gives us a standard deviation of 0.44497. How many cows out of the 20 would you expect to test positive for trich? This is going to be the average. Another symbol for average is expected value of x. So oftentimes when you see the word expect, you should think average. And the formula for average is n times p. This would be 20 times 0.01, or 0.2. What is the probability that at most one cow tests positive for trich? Notationally, this is the probability that x is less than or equal to 1. To find this, we should work it out as the probability that x equals 0 plus the probability that x equals 1. If you look at the sample space, we're trying to say the probability of being 1 or smaller, 1 or 0. I've written in the formula to calculate probabilities for the binomial distribution, along with our notation for the binomial distribution. Let's see what we can fill in for the probability formula. The first thing I'm noticing is that our sample size n is 20. The next thing I'm noticing is that the probability a cow tests positive is 0.01. Let's replace the p's. The other thing I'm noticing is that 1 minus 0.01 is 0.99. Let's go ahead and replace this. We're now ready to work out these two probabilities. The probability that x equals 0 would be 20 choose 0, 0.01 to the 0, and 0.99 to the 20 minus 0, plus the probability that x equals 1 is 20 choose 1, 0.01 to the 1 power, and 0.99 to the 20 minus 1 power. 20 choose 0 is 1. As a matter of fact, n choose 0 will always come out to be 1, no matter what n is. 0.01 to the 0 power is 1. Anything to the 0 power is the value 1. So the probability that x equals 0 is actually just 0.99 to the 20th power. 20 choose 1 is 20. As a matter of fact, n choose 1 will always be n. So we can rewrite this as 20 times 0.01 times 0.99 to the 19th power. Going to the calculator, this gives us a probability of 0.817. What is the probability that at least 2 cows test positive for trig? This is the probability that x is greater than or equal to 2. If you look at your sample space, it's the probability of equaling 2, 3, 4, all the way up to 20. This will take a lot of work to do. There's a shortcut. You should recognize that the entire sample space, including the 1 and the 0, should sum up to 1 or 100%. So out of this 1, if you were to subtract out the probability of being less than or equal to 1, subtract out the 0 and 1. With these values removed, it would leave over the portion of the sample space that you wish to find the probability of. So we're going to use complement rule to find this answer. Now we already found the probability that x is less than or equal to 1. That probability was 0.817. So the final answer here is 0.183. What is the probability that between 14 and 17 cows test positive for trig, non-inclusive? In terms of notation, this is the probability of being between 14 and 17, but not including these values. Looking on the number line, being between 14 and 17, but not including them, would mean including the values of 15 and 16. So we're basically looking to find the probability that x equals 15, plus the probability that x equals 16. I've copied our formula to calculate probabilities from the other page. Let's plug in the 15 and the 16 for x. This is 20 choose 15 times 0.01 to the 15 power times 0.99 to the 20 minus 15 power. The probability that x equals 16 would be 20 choose 16, 0.01 to the 16 power times 0.99 to the 20 minus 16 power. You should type this entire string into your calculator. When you do this, you'll get back 1.47 e negative 26 for the probability that x equals 15, and you'll get back 4.65 e negative 29 for the probability that x equals 16. Let's explain what these two numbers mean. This e is scientific notation. What it means is times 10 to the negative 26th power. Same thing on the probability that x equals 16. This means times 10 to the negative 29th power. So what you really have is 1.47 with the decimal moved 26 times to the left. That's a string of 25 zeros, and then the number 147. For the second one, the negative 29 means move the decimal place 29 places to the left. That's a string of 28 zeros, and then the number 465. This number is so small, you might as well say that the probability is 0. Here are the works cited used in this lecture.